cell voltage, delta G, and the equilibrium constant. In this presentation, we will mathematically relate the cell voltage, delta G, and the equilibrium constant and conduct calculations so we can derive one from the other. We will also learn and derive the Nernst equation and apply it. First, we will derive the relationship between the cell voltage and delta G. We start from our physics definition of delta G being equal to the maximum work possible out of a reaction. And also from the equation that indicates as the maximum electrical work that one can derive is equal to Q times delta V. Now, Q in this case is an electrical charge that is moving through a potential difference, delta V. So V stands for voltage. Okay, and essentially the delta V is equal to the cell voltage, whereas Q is equal to N times Faraday's constant. The units of V are volts, N are the moles of electrons, and Faraday's constant is the electrical charge of 1 mole of electrons. So the electrical charge of 1 mole of electrons, which is Faraday's constant, okay, is equal to the number in a mole, which is 6.022045 times 10 to the 23rd electrons per mole, okay, times the charge of 1 electron in coulombs, gives us a value of 96,485 coulombs per mole of electron. More commonly, we represent 1 Faraday as 9.65 times 10 to the 4th coulombs per mole of electron, or joules over volts times mole of electrons, times 1 mole of electrons. So now we can substitute all that back in the delta G equal to maximum work expression. Okay, and as you can see, the sign now has changed because we want delta G to be negative, okay, whenever the reaction is spontaneous. And so that's why we had that negative sign, because when the reaction is spontaneous, the cell voltage is positive. Of course, the N in this case is the number of moles that are exchanged in the balance reaction, which could be more than one. It could be 2, 3, 5 moles of electrons that are exchanged. Okay, and the calculation of all the units, whether we use coulombs per mole, okay, I mean, if you look at this, I mean, either whether we use moles of electron times coulombs per mole of electron times joules per coulomb, or moles per electron times joules over voltage times moles of electron times voltage, in either case, the units of delta G are going to be joules. Let's now derive delta G for this reaction using the cell potentials. And how do we do that? Well, once again, we go to our standard potentials table. We obtain the right values. We convert the for the species that have been oxidized, we just change the sign of that value. We add up the cell voltage, the voltage of the two half cells, to obtain the full cell voltage. And then we just essentially, once we have that, we just plug the cell voltage in our equation relating cell voltage to delta G. Keeping in mind, in this case, we're exchanging 2 electrons, and therefore the delta G for this reaction is equal to negative value of 2 moles of electrons times Faraday's constant times the cell voltage, which is equal to negative 83.0 kilojoules. Therefore, the reaction is spontaneous. See now if you can come up with an answer for the value of delta G for this reaction. Pause the presentation, come back when you have a value. Okay, here are the values obtained from the table, the potentials table. Of course, changing the sign for the species that is being oxidized. The total value of the cell is this, and now we can plug it in the equation relating the delta G to the cell voltage, and we find that delta G is equal to 89.0 kilojoules. It's positive, which means it's non-spontaneous. So now, see if you can do the same for this reaction. Come back when you're done. Alright, here's the information you need. Changing the sign for the species being oxidized. Here's the total cell voltage. Once again, we just plug it in our trusty equation. Keeping in mind now that this time we have exchanged 5 moles of electrons. And so here is our answer, and it happens to be a negative number, actually quite a large negative number, which makes the reaction spontaneous. Let's now relate cell voltage to the equilibrium constant, and then let's see how the cell voltage, delta G, and the equilibrium constant are all interrelated. So, even redox reactions must reach equilibrium. So, we can combine now the two versions of delta G, one relating it to the cell voltage and one relating it to the equilibrium constant. And of course, since we can make the two equal, and then we can solve for the cell voltage, and given that RT over the Faraday constant is a constant value, and it turns out to be 0.0257 volts, then we can write either of these two expressions, okay, in which one we use the natural log of k, and the other one we use the log base 10 of the equilibrium constant. Either this equation works, and they are included in your reference tables. Before we go on, let's now look at the relationship between these three properties. So if you look at the bottom left of this diagram, we obtain data such as the enthalpy of a reaction and and the delta S and the, in other words, the entropy values from calorimetry and theoretical calculations. And from that we can derive delta G. Once we have delta G, so here, I'm telling you now the typical process by which one will go through all this interrelationship. Once we have delta G, we can calculate the equilibrium constant for reaction at standard conditions, or the cell voltage at standard conditions. And then if we do not have delta G, we can certainly, but we have, let's say, the voltage, cell voltage, or the equilibrium constant, we can relate the equilibrium constant and the cell voltage directly. And how do we get, and where do we get that data? Well, as indicated here in the graphic, we will get the equilibrium constant data from concentration measurements, whereas we will get the cell voltage value from electrical measurements. So using the cell voltage value, see if you can determine the equilibrium constant for this reaction. Come back when you have an answer. So here's our relationship between the two properties. It is just a matter of plugging in the value of the cell voltage in order to get the natural log of the equilibrium constant. Then we solve for the equilibrium constant, which in this case is 1.625 times 10 to the 37, which tells us that this equilibrium is definitely on the product side. And essentially, the reaction goes, I would say, almost to full completion. Calculate KSP for this equilibrium. Come back when you're done. So first of all, we calculate the cell voltage from the table. We obtain values for the potential of the half cells. And here is the voltage for the cell. And now we could proceed to plug this into the equation that relates the cell voltage to the equilibrium constant. And here is our answer. Let's now derive an equation that is very useful. It's called the Nernst equation. Take a look at these three conditions. In the middle we have the situation, the reaction as standard conditions. You have a certain cell voltage. But notice that in the first equation we have increased a product on the left and decreased one on the right. And notice now that the cell voltage is higher, 1.142. Whereas in the third equation, where we have changed the concentration of the reactant to a lower value and the product to a higher value, now the cell voltage is lower than the one at standard conditions. So this could be easily predictable, not the value, but the direction in which the reaction would shift from Le Chatelier's principle. But what the Nernst equation does, essentially, is it computes the cell voltage and any concentration of reactant or product, and at any temperature. So how do we derive that? Once again, if we substitute the two expressions, if we substitute the delta G as standard condition and delta G and non-standard conditions into this expression we have derived earlier in the thermodynamics unit, then you can obtain this value. And if you rework the value, then you get this expression, and substituting in the constant value, then you can derive two forms of the Nernst equation, one using the natural log of Q and the other using the log base 10 of Q. Notice that we're not using K, the equilibrium constant in this case, we're using Q because we're not, when we're describing the cell to start with, we are not at equilibrium. We are on the way to equilibrium. So we're using Q. Just for practice, see if you can write Nernst equations for these reactions at 25 Celsius. Okay, here's the first one. Here is the second one. Notice the expression for the value of Q the expression in symbols for the value Q in this case. Iron is a solid, therefore doesn't show up in the Q expression. And here it is for the last one. See if you can solve this problem using the Nernst equation. Okay, here we are. Now I plug in values, and here's my answer. So will this reaction occur spontaneously? See if you can come up with an answer. Come back when you're done. Well, first of all, let's figure out which species is being oxidized, which one is being reduced. And the iron going to iron 2 plus is definitely being oxidized. So we change the sign. Here's the cell voltage. And now we can plug that value in the expression, the Nernst equation. We plug in also the values of the products over reactants for the Q. And here is our answer, and the reaction is spontaneous. Determine if this reaction is spontaneous as written. Calculate cell voltage delta G and the equilibrium constant. Come back when you're done. Here is the calculation for the cell voltage, and since it is a positive value, 0.82 volts, it is spontaneous. Now that we have the value of the cell voltage, we can calculate the delta G of the reaction, which turns out to be a negative 1.6 times 10 to the second kilojoules. And then we can also derive the equilibrium constant, as you can see here. The equilibrium constant is 5.2 times 10 to the 27th, which essentially says that the reaction goes to completion. I've added some interesting information now in the appendix. I want you to take a look at each slide. However, I will not narrate the slides, and I will dedicate about 5 seconds to each slide so that you can pause it and take a look at it. We have come to the end of the presentation. Contact me if you have any questions.